All right, so we are on air, which means that we can start. So welcome everybody to our cyclic seminar, which is actually taking place on a different day than usual. Our speaker today is Yuri Antipov from Louisiana State, and he will tell us about his work on various aspects of the Riemann-Hilbert problem. Yuri, please. No, it's not. Everything is good. We are on air.
Thank you. So, the title you see quite long, so I will talk about the Riemann-Hilbert problem, but not in a complex plane. It will be a Riemann-Hilbert problem for piecewise automorphic functions and applications to elasticity inverse problems. And if I have enough time, in any case, I will at least briefly mention applications to fluid mechanics inverse problems or free boundary problems. All right, so first, since the title is Riemann-Hilbert problem, in fact, the initial problem is Hilbert problem. The difference is that Hilbert problem normally is on the contour. It doesn't connect the limit values from the left, from the right of the contour, just on the contour, and normally formulated for just either upper half plane or lower half plane, or certain different region. So the formulation is quite long. First of all, we describe the domain. It is a circular domain. You have a complex plane with n plus 1 holes. All the holes are circles, disks. And then on the boundary of these disks, we prescribe some further continuous functions, a nu and b nu, and also c nu. And for generality and for applications, it's very important. We also assume that these functions are not continuous. Everywhere they piecewise further continuous. So there are n plus 1 points for, it could be actually n plus 1 contours, but on each contour we have a certain set of points where these functions could be discontinuous. We remove the singular case when both functions a and b on the contour vanish. And what we need to find a function phi with a real and imaginary part.
So it's not possible to take limit infinite number of such jumps. It always must be finite.
So what?
With number of jumps, it always must be finite.
Yeah, it's fine.
It will not work if you take limit.
No, the number is finite. Yes. So, and then we need to find a holomorphic function in the exterior of these circles, which is further continuous up to the contour, except at these points of discontinuity of the data, and which satisfy the boundary conditions. Real and imaginary part of that unknown function are prescribed through this linear relation. And for convenience, we denote all the points of discontinuity as set T. All right. Now, the background, some references. The history of this problem is long, and I cannot, of course, mention all of them, all the references. So, most related to the subject, the work by Aksentiev, no solution in the form, the modern form, but at least there was existence, uniqueness, and he actually considered Schwarz problem in the very beginning and introduced symmetry method. Then Chibrika-Silvestrov considered main ingredients that I will use, and this quasi-automorphic and quasi-multiplicative analog of Cauchy kernel. Method of successive approximations was developed by Mitushev and Rogozin. And then with Darren, we found that actually it was his idea how to connect Schottky climb function with quasi-automorphic analog of the Cauchy kernel on circular domain. And Sylvestrov introduced me into this subject, and we wrote several papers about this method of Riemann-Hilbert problem on circular domains, and found applications in cavitating flow and also multiply connected, physical electromagnetic problem for plate with Hall effect when the electrode and isolate not prescribed everywhere. All right, now first how we can solve the problem. Just general theory. Of course, I will not go through all the proofs, but just some important results for understanding applications. So we have again circular domain. L0, L1, Ln are all circles. We introduce generators. Sigma j, it's a composition of two maps. It's a Möbius map. T for we can choose any circle, for instance L0 as a major circle, and call it T, map, Möbius map T0 as T. And if we use only one map, then we of course will not have analytic function because of complex conjugation. If we apply a second time, then we have meromorphic map. And if we use as generators, we can, if we apply only sigma j, then we map all the exterior, the exterior of all these circles into the interior of the contour L0, and in this way we can, if we add also the boundary of these circles, then we will have a fundamental domain that consists of domain D itself, and also image by T of D, and the contour L, that is set of all contours. But if we consider infinite, if we design any map sigma, which consists of even number of maps that are introduced, then we may basically cover the whole complex plane apart from the limiting points. So we see we map inside of the interior, then map again in the interior of each circle, then go back and forth. And then if you have only two circles, then we have only two limit points in each circle. If you have even three or more, then the number of limiting points is infinite. All right. So, and this, of course, restriction, K2 doesn't equal K1. It's basically not a restriction because it will not, they will just cancel. If two maps, the indices are the same, then it's identity, so we don't need that. Now, we set topology. Now, a function. Since we need to find a function, now we need to extend the function in all these domains. So, in general domain D, in the exterior of all these circles, disks, we have phi of Z small, and then we extend them by symmetry. And since we also require automorphicity law, so in this way, we basically extend the original function phi of Z from domain D into the whole complex plane apart from the set of limiting points. And apparently that new function is invariant with respect to this group generated by these transformations, and also satisfy the symmetry condition. So that symmetry condition basically is generalization. If you're familiar with for instance, in application elasticity, you have problem for half a plane. It's very common to extend the function by complex conjugation to the lower half plane. So that is, and then if you have one disk, it's also in regular elasticity, for instance, books explain how to extend it in the exterior of the disk, like a Schwere book or England book. But if we want to do it for at least 2 disks or more, then we use this symmetry condition, just generalization. Now, we need, so idea is to use a Hilbert problem and formulate it in the very beginning to Riemann-Hilbert problem. So we call phi plus is the limit value of the function of z from the, when the limit goes from D, from the original domain, and phi minus is the limit of function f of t of d. So from, if you consider just fundamental domain, it's from, it goes to the same point, but from the interior of the domain t of d. So for each disk. So in some sense, I mean, it's still left and right limits. In this case, it's left, and then we prescribe direction. Plus from left, minus from right. And now the boundary conditions that I formulated in the very beginning, it's a Hilbert problem, can be equivalently reduced to a Riemann-Hilbert problem boundary condition with new coefficients. And then the absolute value of P of t modulus is 1. So it's very important for simplify this derivations later. Now, for solution of Riemann-Hilbert problem, we need factorization of the coefficient. So it is a canonical function, it satisfies certain conditions. Even if you don't have canonical function, but at least factorization, you can adjust and use it. But in this case, canonical function has certain features which are standard, like feature property 2, it's requirement that that function has to factorize a coefficient. Then property 1, it relates to the property of the solution to be discontinuous, and that is why, I mean, the coefficient is discontinuous, and the solution may have a power singularity. That is why that canonical function also it means power singularities. But also, since we continue symmetrically our known function into the whole complex plane, so that should be symmetry condition and also multiplicativity condition that is not exactly required in the very beginning, but is convenient for the next step. So basically, we require that this canonical function has this coefficient. It gains the coefficient when we apply the map sigma. All right, now a quasi-automorphic analog of the Cauchy kernel. So the Cauchy kernel, first of all, has to satisfy the Schottky formula. So condition 1, it means that we have at least a standard Cauchy kernel. Then property 2, basically, it's not a requirement, it's just a property. Since it's a theorem that we proved, it's about the existence. So we say that such function exists, which satisfies property 1, property 2. There exists a point in the fundamental domain when kernel equals 0 for all t. Then property 3 is about quasi-automorphicity. So because we have again this group generating and generators, so if a generator applied to Z, then we don't have the same kernel, but we gain some additional term. And at the same time, from that kernel, for first class group, when we know that the convergence exists, then we can write it in the terms of series. But in fact, such kernel exists regardless whether the series is convergent or not. It's just a tool for computation. And it is possible to prove that such function exists by using Riemann surfaces, because we can, if you have the circle domain, we can design a Riemann surface and then use theory of abelian integrals and show that abelian integral of second kind, which has actually kernel k, exists. And if we add property 2, then it's unique. If you divide by 2 pi I, then it design a B canonical homology basis. And then we express this kernel through the Schottky Klein prime function. So basically that representation is also unique if we want to satisfy all these conditions. All right. Now, it was definition, but now we need and that was given not for our problem. Our problem, as we remember, we need also symmetry, and also it is has a certain discontinuities. I mean, power singularity cause discontinuities. So now it's a multiplicative canonical function. How to write it, and we proved that, or found algorithms that canonical function can be expressed exponential function of two gamma functions, not Euler integral, but just gamma function, and that gamma function expressed through the integrals of, so instead of log p, because absolute value p is 1, you have just argument, and then that extra term is due to the discontinuities we have, and if you have this discontinuity, take exponential function, we have a power logarithmic singularities when we analyze Cauchy kernel, I mean the right second part and the first part, and then we will have singularities we need after we take exponential function. So basically, it's an ingredient that we need for the solution. But it's not enough. We need another tool, since we need to solve the inhomogeneous problem. If we use only a quasi-automorphic analog of the Cauchy kernel, then we end up with Jacobi inversion problem. And we prove that there exists another analog of the Cauchy kernel called quasi-multiplicative analog. So first of all, satisfy the Schottky-Plemer formulas. Then it also there exists a point where this kernel equals 0. Then there is also quasi-automorphicity property, but now we have extra factor h sigma. So in this, the previous kernel had just m and m on the left and the right. There's no h. Now we have h, and that is why we call it quasi-multiplicative analog. So the construction of this extra kernel allows to avoid the Jacobi inversion problem.
So again, what is h? It's operator or it's function? What is h?
Oh, h is basically a group homomorphism from a group that we call here G to the multiplicative group of complex numbers. So if we satisfy the conditions that h of sigma omega, where sigma omega element of group G equals h of sigma multiplied by h of omega. So in other words, we have actually, it's in the representation of the series, it's a complex numbers, and means that we apply the transformation sigma, then we will have just multiplication of these factors for two different generators. All right, now the solution. We know canonical function. So we factorize the coefficient, do this usual routine for Riemann-Hilbert problem. Then introduce, when we need to take care of the right-hand side, we don't use kernel k, we use m, this quasi-multiplicative analog. And then we write the solution using Liouville theorem for multiplicative functions. It's in Krauss automorphic forms book. It's this theorem is presented. And of course, since we have lots of different poles and so on, we need to write the general form of the rational function. In this case, it is omega. And to express this quasi-multiplicative analog, we cannot use, of course, just rational functions, because at the end of the day, we need to take care of symmetry and automorphicity. So we need to work only with functions which have potential to be automorphic. So of course, that form of solution, if we just take arbitrarily see the coefficients and all the constants arbitrarily, then we will not have automorphicity. We need now to check the automorphicity of the solution. So, and then we just say, well, the function has to be invariant. So we know the property of the kernels, K and M, and we write a condition of an invariance of the function phi with respect to the group G. It gives us n conditions. Then, since we have discontinuities and power singularities, let's say even for standard integral problem, we always have these indices, because the argument of a function passes through discontinuity. Each time we need to fix a branch again and make sure that we have power singularities in the range which guarantee the integrability of a solution. So that is why we have extra conditions. It's here. And yeah, also this condition 3. It's still, I mean, condition 2 and 3, they come from the requirement the solution has to be integrable at the discontinuity points. And we have also one group condition that guarantee automorphicity. Now we introduce total index, kappa, and also this other numbers which we obtain. And again, we took care of this integrability of solution at each discontinuous point. And using this kappa, we can formulate the solvability theorem. So if that total index kappa greater than 2n minus 2, then the Hilbert problem formulated is solvable and has such a number of arbitrary real constants. This is solution. And if kappa less than 0, then solvable if you have a certain number of conditions solvability. So basically, that is a formulation in the, that is quite common for any Riemann-Hilbert problem theory in any class. All right, so that is just, I went through the theory, of course, didn't prove anything, but just gave you some background that I used. Now, two examples. First, inverse problem of anti-plane elasticity. That is some sense simpler than the second example. And first formulation. Again, we have n inclusions, which, but now they're not in circles. I mean, the contours are not circles. So we have just n inclusions. Inclusions means, in this case, that we have it's an anti-plane elasticity, so it means that we have a plane, cross-section, plane, and there are some contours which are boundary of these inclusions which are not known. We know that shear moduli of inclusions in the exterior are prescribed, and in inclusion and in the solid are prescribed. They're different. We assume that the inclusions and the matrix, the exterior, are in ideal contact. Then at infinity, there is certain constant shear stress applied. And what we want to find the shape of these inclusions such that the stresses inside the inclusions are constant. So it means that we have a structure with all these inclusions with different shear modulus. Then we apply stress at infinity, shear stress at infinity, and want that inclusions don't even care about the stresses at infinity. So in other words, they're uniform. And so that is elastic formulation. Now, mathematical formulation. If U and Uj are displacement components of the vector in the exterior and the inclusions themselves, then the stresses are derived with respect to x, let's say t1, 3 and t2, 3, and x1 and x2. So basically, two derivatives form here stress tensor, because it's antiplane stress, antiplane deformation. Right. So since stresses in infinity are constant, then the displacements can be immediately recovered at infinity and have this asymptotics.
Yuri, quick question. What are the x3 components?
X3 components, it is, yeah, you have a body, it's like a cylinder, and then you apply, so that is x1, x2, x3. Right. So you apply in direction x3. So if it is x3 is normal to the plane,
Okay.
and then just all right, I'll do it in different way. So you have x2 normal, x1 and x3. So that is sigma 2, 3. Right? So it shears, right? So it's applied not in the plane, it is cross the plane,
Okay.
like scissors. And then you have here in fact x1, sorry, z is x2. So you have, yeah, so that is x1 normal, and then component in the x direction gives us sigma 1, 3. So here we have x2 normal, and then x1 and x3. So that is sigma 2, 3. They apply everywhere in the infinity.
So those displacements in the x3 directions are themselves functions of x1 and x2 only.
You mean this one?
No, the,
Yeah, displacements in only one direction, x,
Okay.
yeah, in direction of z.
Okay.
So that is why we have only one component.
But depend on x and y.
X1.
So again?
But they depend on x and y.
Oh yes,
Oh,
yes, yes,
okay.
yes, because you see, everywhere in the plane they differ,
Yeah.
but they act only in direction of z. Okay, and then since we want the stresses to be constant inside of each inclusion, and they constant not just like an infinity for the external body, they constant everywhere at each point of the inclusion. That is why we can recover the displacements up to arbitrary constants at any point in each inclusion. So the Uj are described now by up to arbitrary constant. And that constant, by the way, very important. Now, the boundary conditions. The boundary conditions, it's ideal contact, so it means that on the boundary, our inclusion of each inclusion and the matrix of the exterior, the displacement have to be continuous, it's the second condition, and also stresses have to be continuous as well. But for in the sense of normal derivatives, it means the normal derivative are discontinuous. Yeah, so I use only two stresses. I mean, sigma 1, 3 for infinity, also for interior, but on the boundary, since you have arbitrary domain, so we use curvilinear coordinates, and that is why that is a condition for stresses in direction z3 with normal nu, so the stresses are continuous. It guarantees that there is no sliding between, there is no sliding for each inclusion. Now, I didn't say that the displacements are harmonic functions. Yeah, it comes from elasticity. All right, since we have a harmonic function, U is harmonic function, it is natural to introduce harmonic conjugate and then design an analytic function, phi of z, not only phi of z for the exterior, but phi j of z for interior. I mean for, not touched. Okay. And that two conditions can be, it's just a simple algebra, you can rewrite them in terms of functions phi and phi j of z on each contour. And it's also convenient to, yeah, first of all, phi j of z, it is interior for each inclusion, since we know uj, we know vj by Cauchy-Riemann conditions. So phi j of z up to arbitrary constant, but now it's complex constant, is known. And so phi j of z is written, and then if we introduce a new function, f of z, instead of phi of z in the exterior, which connected with original function phi by this formula, then for this function we have a very simple problem. The boundary conditions, these two boundary conditions can be replaced by this condition. So we need to find analytic function phi of z in the exterior of these inclusions when it is prescribed on the contour. You know that if you know the shape of the contour, then this problem is ill-posed, because if you're looking for analytic function on a prescribed contour, in a prescribed domain, and on the contour you prescribe the function itself, so such a function in general doesn't exist. But since we don't know the shape of the contour, so it means that we want to satisfy this condition and also recover the shape of the contour. So that is why we call it the inverse problem. Okay, so the idea is to use the conformal map from a canonical domain, circular domain, into the domain, the physical domain. Such map exists, certain restrictions, degree of freedom, depending on multiplicativity domain. But you see, all the previous transformations were useful because you see the unknown function z that will give us, then we introduce z omega of z, is in the real part only. So if we take the real part and then imaginary part, we can split our problem into two independent problems. Take imaginary part first. If you take imaginary part of f, then the first term is 0, and we only have aj. So, and then we take a real part, and we already know function f of z, in a parametric domain. Then we can find the conformal map. It is now two Schwarz problems. We introduce a function f of z, f capital of z, that is basically the same function f, but f of z. So you see that is unknown function. We don't know omega yet, but we can say, well, we call it f of zeta, and take imaginary part, and it's just a of j, and we can solve this problem, find f of z. Then we go take the real part, and since we know a real part of f, we know we have a new Schwarz problem and can solve it and find omega. So that is basically the idea. All right. So the theory I presented in the first part now, of course, simplified because we don't have discontinuities, but we have the right-hand side. So we need some elements of the theory I present. So for the solution, we introduce again a new function phi z, just convenient to get rid of pole at infinity. Then we extend, use again the same generators, because now we're in circular domain, and then we will have a Riemann-Hilbert problem. For a very simple Riemann-Hilbert problem, you see only jump here on circular domain. And so problem 1, it's when we need to find function f, which is now phi 1. We use the kernel K of series representation, quasi-automorphic kernel, find the solution. And since the kernel is not automorphic, it is quasi-automorphic, you have extra terms. So that is why our solution, when we write the solution, is not automorphic. And it is automorphic if and only if we have a certain condition. It is written here. So that is the condition. We find the solution, phi 1, then we look what is going on with this function if we apply this map. And it has to be the same, but it's not. You have extra terms because of the property of the kernel. And then we look at the value of this extra terms. It has this value. And it turns out that the solution is automorphic if and only if that guy equals 0. So in other words, imaginary part of this equals 0. And it gives us a condition for arbitrary constants. We have two groups of arbitrary constants when we integrate it, transform the boundary conditions of physical problem. So we can, of course, just leave it like it is, but that part, for instance, can be simplified. So that is expressed through the this Cauchy kernel analog, and we can look carefully at the position of poles, consider different cases, and simplify this condition in this one. So this means that we can find all the constant through 1a0, that is arbitrary, cannot fix it, and this is free of arbitrary constants. So for this case, for this step, we need the kernel to be absolutely convergent, because we actually we change the order of integration, summation, when we use theory of distance. I think it's possible to overcome this, but then, of course, we will not have such a simple representation for the arbitrary constants. If you don't want series to be absolutely convergent. Then the second problem basically is the same, but the right-hand side is different, more complicated, because now it has function f of z that we recovered from the first step. So we write the solution in the same manner, and of course we again have extra arbitrary constants. We satisfy the conditions and recover these constants. So basically that is the solution of the second problem. We don't need solution for the first problem to construct the map. The solution of the first problem is auxiliary problem, because if we don't know f, we don't know f2, phi 2, and phi 2 directly expressed through the conformal map. So you see now the conformal map is expressed through the solution of the second problem. And then the standard thing, we let psi go around these circles, L1, L2, and so on. And then the image by omega is exactly the shape of the contours. And now I want to emphasize that arbitrary constants we gained in the very beginning. Remember, we had stresses at infinity. Then when we recovered displacements inside of each inclusion, we integrated and we had certain arbitrary constants. We call it d1 or dj. And then we design an analytic function. We use a real part in those constants and harmonic conjugate that also gave us arbitrary constant. So those arbitrary constants, if we disregard them, then we will not have a solution. So those constants were quite, very important because they, the presence of these constants, d1, j, and d prime j and d double prime j, allowed us for satisfying the homomorphicity, automorphicity conditions, and in this way we have a unique solution up to d0 prime and d0 double prime. So, but it's basically doesn't give us new shape of the contours, some kind of global translation of the system. Right, this a couple of examples. Symmetry inclusions. You see, for this inclusions, I choose shear modulus smaller than shear modulus of exterior, then we have this convex part. But if you do it opposite ways, it will be turned around. So it's for two cases. In the symmetric case, if you have not symmetry, there is no unique solution here, because basically we need the question is find the family of inclusions which satisfy these conditions. And since we have lots of parameters, we can change the parameters and have a new shape. So if we choose here, put here an example. All right. Now the third part is supercavitation. So that is, of course, a nice picture. Derivations not very close to what you see here. But it's a typical cavitating tunnel. Normally they're not very big. So we put a cavitator, then fluid goes substantial speed, and then you'll have bubbles. Right? You increase speed, increase the area of cavitator, then it could be larger, longer cavity. And that phenomenon is used for different purposes. The most harmless use of supercavitation is cleaning of medical devices, medical instruments, because when bubbles hit the surface, immediately remove all this dirt. Then classical and original applications, cavitation was in study of propellers, ships, because they're huge and also have cavities. It's not actually super cavitation, cavitation. And when the bubbles collapse and do it for months and even years, then the surface of the propellers is damaged. And then, of course, military, they always find interest in such things. So, experimental results. Yeah, if you look at the supercavitating, the cavitating tunnel, you see that the process is stable. The shape of the cavity is not changed with time. If you don't change the speed, so the shape of the cavity always the same. And only bubbles change the position a little bit at the area part or downstream. So there is kind of re-entrant jet. You see it go back and forth, but the rest is stable. So also the theory largely depends on the so-called cavitation number. That is dimensionless parameter. P0 is pressure inside the cavity, it's considered constant, and P is pressure in infinity and far away from the cavity. V0 squared is speed on the surface of the cavity, and rho is density of the fluid. Okay. Now, Bernoulli paradox. You see, we have a cavity, but it's like a bubble, right? You have, but it's not really a bubble because it has a hydrofoil. Could be hydrofoil, could be wedge, could be anything, right? Assume that hydrofoil. So, or wedge. Then it goes, hit the surface, then it goes around. So velocity vector is parallel to the plates, and then separation, and then there is a cavity, right? And here V is constant. Pressure also constant, right, on the cavity, and inside also. Simply, it's a model. Now, if you assume that here the cavity is closed, means that it's closed, it means that there should be a stagnation point, right? The stagnation point. The stagnation point, V is 0. So, but if V is 0, then Bernoulli's law says that P is infinity. That is nonsense, right? Because it's constant. So that is why here, when we have a rigid boundary, we don't have this paradox. P is constant, but V is varies everywhere, so it's not a problem here. But here it's a problem. You cannot assume that you have stagnation. So that is why the cavity cannot be closed, it was always open. And all models of cavitation are about how to model the closure point. And lots of models, starting probably Rebushinsky in 1920, and then lots of other models. And the most sophisticated, at least in the two-dimensional model, probably the most successful was Turing model. You see, it is agree with all these conditions, but at the area part, you see, we assume that the function W behaves in this way, quite unusual, right? It's not about Z, it's not a mistake, it is W. So the local derivative behaves as a function itself minus W0. W0 is the value of the complex potential here, minus 1/2. So first of all, that model, ideally, I mean, at least looks nice. When you solve the problem, you'll have this infinite spiral here and here. They also there are two models, single spiral vortex model and double spiral vortex model. In fact, they have both two vertices here, but double spiral vortex assumes that weight goes to infinity, and single spiral vortex assumes that points is just one point. In some sense, it's like closed, but with this condition. And it's still some kind of course discrepancy in both models, but single spiral vortex model more interesting because it gives Riemann surfaces automorphic functions for when we have double, triple, and more connectivity domains. And if double spiral vortex models, because the weight goes to infinity, then the whole domain is simply connected. Because at infinity they all connected. All right. So
if there is a single, there is with power 1 minus 1/2. If it's double, what's the singularity? Or it's the same?
What is the same again?
You have this single and double spiral model.
Oh yeah. For both they have the same.
For both.
Yeah. But again, connectivity is different. And
As you go
also,
in the spiral, do you get alternating air and water? I just don't quite understand it. If you take the earlier bit of the streamline,
yeah,
you've got air on one side and water on the other side. And when you roll that up, you're getting alternate layers of air and water. But you're
and
still calling
to
it vortex.
overcome this, some people just ignore it. We wrote some kind of model of Riemann surface, assuming that how it's going. So it goes inside, but not all streamlines. In fact, we computed them. So it close, next streamline, next. At some point, next streamline goes just around and leave without any entrance inside. The previous go inside, and that mechanism is modeled by using Riemann surfaces. So next, each streamline goes and pass to because logarithmic function. So we use logarithmic function for modeling a Riemann surface and goes to a certain number of sheets, and then returns and leave. And only one line that is the boundary of that cavity that goes inside through all infinite sheets and through infinity again and leave. But it's only to adjust only the mathematical picture to the physical reality. The previous model by Gilbert, Kreiser, and so on, they didn't use this model. They use also two-sheeted Riemann surfaces. They also admitted that the jet close to the boundary goes inside, but double connected, two-sheeted surface, and then leave. So without Riemann surface, it's impossible to do it. But in fact, again, it's that area, whatever you use, it's just bubbles inside. So, but mathematically, that is convenient. Later, Terentiev added two additional conditions, but because that condition was still enough, Terentiev didn't solve the problem. He just suggested to use this asymptotics. And then it was found that that was not enough for the existence uniqueness. We needed two more constants, and he suggested, first of all, why not to put arbitrary constant and recover it? So it was one generalization. And second, that there should be some gamma circulation. There should be circulation that should be arbitrary. So we need to add circulation as a free parameter and recover the circulation. All right. So, yeah. So that is some work that close to this model. As I said, Terentiev added some constants and found a solution for a single supercavitating foil and numerical results. Then with Sylvester, oh, I'm sorry, it should be Sylvestrov, not you. Sylvestrov and me, we considered two cavities, supercavitating hydrofoils in the channel, but no numerical results, quite complicated. And with Anna Zemlyanova, we did it for free surface and one wedge below the surface, and then use machinery Riemann surfaces. So it's basically only one numerical, one problem that was solved numerically up to the end. It's quite complicated, not because of the conductivity, because lots of free parameters, they're all involved, and when we use a conformal map and recover it, you need to solve transcendental equations, recover these parameters. Numerically, it's quite hard. But for a double connected case using the Riemann surface, we managed to do it. So that is why what I'm going to discuss next, maybe just 2 minutes, it is not about the numerical solution or only just a theorem. We have like n now wedges, all cavitating, and then we can use the theory of automorphic functions. So again, no solutions, just how that problem can be mapped to this Riemann-Hilbert problem of automorphic functions. So we have conditions. So the boundary of each cavity and hydrofoil is streamline, so the first condition. Then on the boundary of the cavity, the speed are constant. It's another second condition. Yeah, this condition. But on each cavity, of course, we have different V. And then the third condition, it's because we know the geometry of the wedge. So since streamline also tangential to the hydrofoils, so that is why we know argument of the complex potential derivative, that is velocity with minus. So, and yeah, it's for two different cases because the wedge could be stagnation point here or stagnation point here. That is why we have two different possibilities. And now, probably the last slide, and I will hope my conclusions. So conformal map, this is basically Chaplygin idea, but maybe it was even before in the form of Soviet called Chaplygin, maybe it goes even earlier or somewhere else. But anyway, so for free boundary problems, very convenient to, if you want to find a conformal map, you basically need to find the derivative of dz by dz. Zeta is parameter. And at the same time, you can represent as a quotient of two functions. One is complex velocity, and second derivative of the complex potential with respect to parameter. And in this way, you can represent the original derivative of the conformal map that is unknown as a product of two functions. And since we had the boundary conditions, either the argument of the derivative or the absolute value, then using these two functions is very convenient because now we immediately linearize the problem without any, without sacrificing any boundary conditions. It's exact. Yeah. So, and yeah, I will probably not go it, so, but maybe just show here. You see, that is this condition, and derivative, which you see a log of function. We know that the absolute value of this derivative, or we know argument. If you know absolute value, it means that we know the real part of that. If you know the argument, we know that we know the imaginary part. In this way, we naturally have real and imaginary part in certain part of the contour. So, and this one even simpler. And since my time is over, I will just skip all that. Basically, we need to go through all this stuff and my conclusions. So, in the first part, I presented the theory of Hilbert problems for multiply connected circular domains with discontinuous coefficients, quite complicated. And solve the problem in terms of quasi-automorphic, quasi-multiplicative analogs. This approach gives exact solution and it gives us a chance to bypass Jacobi inversion problem. Numerically, it's important. Then illustrated this approach for inverse antiplane elasticity problem through solution of two Schwarz problems. Consequently, they were solved consequently, one after another one. Then I just describe a model for supercavitating flow past n+1 wages, no solutions, but at least gave an idea of how the problem can be reduced to Hilbert problem and then be solved. And the map that we don't know in the first and second problem, elastic or fluid mechanics problem, can be expressed through solution of two Riemann-Hilbert problems for symmetric piecewise automorphic function with continuous or discontinuous coefficients.
Right, thank you. Well, we might have time for one or two quick questions, comments.
If two of your circles are close together, do you get a singular limit where you have to be a bit careful because something cancels out or things get a bit delicate?
Yeah, of course, the closer you should expect some numerical difficulties. I would say that for real applied problems, nobody found any limit when either series representation or successive method of successive approximation is divergent. Everybody agrees that convergence, you need to take more elements of series. With Sylvester, we found an example when the series is not absolutely convergent. But again, it was a little bit artificial. I cannot even design a real problem, but it's still symmetry Schottky group. But yeah, one is infinite circle, and then you have symmetric 16 circles and so on. But lots of Kleinian symmetric groups, no symmetry, Klein groups which generate series which have a certain limits when they not absolutely converge.
Just in the theory
But
of
numerically,
composites,
nobody said, well, if you have a very, very close and it diverge.
because in the theory of composites, it's a big deal when the bits get close, and there's a huge theory going back to Keller and others.
What I'm saying, yes, it was.
Yeah.
I would say it goes back to the beginning of 20th century. There was lots of theoretical work in Finland and I don't remember in Germany probably, and it's actually spread for the whole century. People do it back and forth. So lots of examples when the series is not absolutely convergent, but numerically for problems like that, nobody found. So well, you see, you have 10 to the sums and then so more likely, it's all these conditions are sufficient.
Other questions, comments, Oleg?
In the last problem, where you had real part on one part of the circle, imaginary part on the other circle, if you actually use a 1/2 singularity, then can't you make it into a bunch of 1/2 singularity corresponding to points where you have change of boundary condition? Wouldn't you turn it into a problem for just the real part of given real part of analytic function on the boundary? So you could put a bunch of branch point, 1/2 branch point on the boundary. So then the condition that the original part is it switches between real and imaginary part, that switch is not detected anymore for the new function.
You have, you see, it's a natural generalization of a problem for, say, just one slit. If you have a slit in a complex plane, you have Dirichlet condition on slit, and by symmetry you put a Neumann boundary condition on the extension. So you have a upper half plane. So it's a typical Hilbert problem. A real part on the segment -1,1, and Neumann boundary condition from -infinity to -1, from 1 to infinity. You will have a square root singularity. There are different techniques to deal with it. Standard technique, you just write -1/2 singularity immediately, and kappa, you don't even know, you just complete the theory, and then at the end you see whether the solution is integrable. Now you have bunches of them, circular domains, but the idea is you introduce unknown singularities, but they should be integrable. And then you solve the problem, look at them, and make sure that they're integrable. With branches, I think it's also possible if you said you put in branches, but basically you will just reduce to continuous coefficients, right? Yes, it's also in the Gaffel book, they have this also approach. But basically, if you reduce it to continuous coefficients, you need to compute this jump, which, so you do it in the very beginning, but not at the end. When you have bunches of circles, lots of different conditions, it's hard to predict.
All right, I'm afraid our time is up, so let's thank Yuri one more time.